Okay, so now let's talk about IBM Model 1. The critical question is, how do we define a model, P of F given E? So we might, for example, have an English sentence, like the dog barks. So this is E. And this is a French sentence, say this sentence here, which I believe is a reasonable translation into French, although my French is terrible. And so we want to assign this pair of sentences a conditional probability, or more generally, this is one of many possible translations for the English. We want to define a distribution over all possible French sentences paired with this English sentence. I'll assume throughout that each English sentence we're looking at has L words, and the French sentence we're looking at has M words. So M and L, the length of the two sentences. So you might try to model this probability directly with no intermediate structure, but that turns out to be a very difficult thing to do. And so an absolutely critical idea in the IBM models was to define the idea of what's called an alignment between these two sentences. Okay, so in this case I have number of French words M equals 3 and the number of English words L equals 3. And an alignment is just going to be a sequence of values A1, A2, up to AM. A is 3 in this case. And it basically, for each French word, specifies which English word it's aligned to. So here's one possible alignment. We could say le is aligned to the, this word's aligned to this, and this word is aligned to this. Okay? So more formally, any of these alignment variables can take any value in 0 to L, where L is the length of the English sentence. I'll talk in a second about why we have 0 included here. But for this particular alignment, we have A1 equals 1, A2 equals 1, A3 equals 1. Why do I have 0 as a possible alignment point? So if I say, for example, A1 is equal to 0, that means we actually assume that this word is aligned to what's called a null word. And so the IBM researchers found it was useful to include this extra word, null, which could be used to generate some French words in the sentence. Intuitively, this corresponds to French words for which there's no natural word to align to in English. Okay, so how many possible alignments are there? So if I have M possible words in, L words on the English side, E is over here, and I have M possible words on the French side. Each of these French words can be aligned to 0, 1, 2 up to L. So there are 1 plus L or L plus 1 possible alignments for each word. And because I'm choosing an alignment for each of the M words, we have L plus 1 per M as the number of possible alignments. So an alignment can be any structure where each French word is aligned to a single English word. So here's an example English-French sentence. In this case, the number of English words is 6, 1, 2, 3, 4, 5, 6, and so L equals 6. Number of French words is 1, 2, 3, 4, 5, 6, 7, so M equals 7. And one alignment is the following, so let's number these English words. 1, 2, 3, 4, 5, 6, and the French words 1, 2, 3, 4, 5, 6, 7. And so basically an alignment is going to be a sequence of numbers, 2, 3, 4, 5, 6, 6, for example, specifying word by word in French which English word we're aligned to. So this is saying that word 1 is aligned to word 2 in English. Word 2 in the French is aligned to word 3. Word 3 in the French is aligned to word 4. Word 4 in the French is aligned to word 5. And then the next 3 words are all aligned to English word 6. Okay. So that is one possible settings for these alignment variables. And that's probably a pretty good setting for the alignment variables. Okay, it does a reasonable job of saying what the various words in French correspond to on the English side. So that's one possible alignment. let me show you another possible alignment. So this one down here is just saying that every French word is aligned to English word 1, so we can draw it like follows. Okay, so again, each French word is aligned to a single English word. In this case, they're all aligned to word 1 on the English side. This is clearly a very bad explanation of the translation in this case, so it's a very bad alignment. So the next idea will be to define a model which assigns a conditional probability to any alignment A paired with a translation F, conditioned on two things, conditioned on the English sentence and on the length of the French translation. So you can visualize this as follows. We might have some English sentence, for example, the dog laughs. And let's say m is equal to 3, and so we know there are 3 French words, F1, F2, and F3 in this case. Okay, so each of these words could take any value in the vocabulary. So we could have all of these different words in French. And so that's one choice. For each of these positions, we're going to choose a French word. And in addition, we're going to choose an alignment from the space of possible alignments. So for example, we might have, as I showed you before, this alignment with the words le, and this, and then this. And that would be one particular choice, and so that would have probability of, the alignment in this case would be 1, 2, 3, sorry, 3, and it's be conditioned on the dog laughs and on the fact that the French translation is also of length 3. Okay. We're actually going to decompose this into a product of two models, and we'll describe soon how we can define these two models. The first is going to be a distribution over possible alignments. So conditioned on just the English sentence and on the length of the French, we're going to define a distribution over all possible alignments. Remember, there are L plus 1 to the power m possible values for A. And then secondly, we're going to define a second model which, conditioned on alignment, an English sentence, and an English sentence length, assigns a probability to each possible French translation of that English sentence. Once we've done this, we can recover our sort of end goal, which is to define a probability of any French sentence given an English sentence, and we can do this just by summing out over all possible alignments. This follows by the usual rules of probability. So this entire product here is P F, A given E M, and by the usual rules of probability you can marginalize out this alignment variable. You can sum it out to get a model of P of F given E. Okay, so that's the basic trick in introducing alignments in these models. It's a very important thing to do. It allows us to introduce these intermediate variables, alignments, which give us an explanation of the translation process. And as we'll see, we end up with very natural parameterizations of these two models. And we can then sum out over the space of all possible alignments to get this final distribution over F if we need to do so. So the bottom line is estimating the probability of F given E directly is very difficult. So instead, we come up with a model of P of FA given E. Sorry, this should be conditioned on the length, I guess. And then we say P of F given EM is equal to the sum over A P of FA given EM. Now, a very important byproduct of this process is that once we have a model of this form, we can actually, given an English sentence and a French sentence, we can find the most likely alignment. So if we have some English sentence here, and we have some French sentence here, we can, for every possible alignment between these two sentences, evaluate their probability and pick the most likely alignment. And so we do this by, again, using usual rules of probability. We can say that P of A given FEM is this model term on the numerator, and then on the denominator I have a sum over all possible alignments. This is P of F given EM. And again, this equation follows by the usual rules of probability. And then for a given FE pair, we can find the most likely alignment amongst the space of all possible alignments. I'm not going to go into detail about how this is done. It's described in the notes that I provided to accompany this class. But you can actually, under IBM models 1 and 2, compute this most likely alignment very, very efficiently. In fact, nowadays, the IBM models are rarely, if ever, used for actual translation. Even though they were originally designed for translation, they are rarely used for translation. But they do play a critical role in allowing us to recover alignments between sentences. So once we've trained the parameters of an IBM model, we can then, sentence by sentence pair in our training set, find the most likely alignment for those sentence pairs. So here's an actual example. This is for a French-English translation using some of the IBM alignment models or translation models. So here's the French, here is the English, and here what I've shown is the most likely alignment. And so what we actually have here is, in fact, for each English word, we have its alignment to a French word. So in fact, this model has been trained in the opposite direction, PE given F, and we have a sum over alignments PEA given F, this kind of model. So it's trained in the reverse direction, and because of this I have an alignment now where each English word is aligned to a single French word. So let's look at this. It's saying that the is aligned to le, which if you know French and English is pretty much correct. Council is aligned to this word, and so on and so on. So these alignments actually are quite good, and they become very important in the phrase-based translation systems we'll see in the next couple of lectures of the class, because they essentially give us an anchor on how words in the English are aligned to words in the French. Okay, so bottom line, once we've trained IBM models 1 or 2, we can look at our training data sentences, which consist of these sentence pairs, and actually find these most likely alignments. And at that point, we have a much better handle on how these two sentences correspond to each other.